Hi, everybody. It's a real pleasure to introduce Paolo Serra, which is one of my favorite speakers.
No pressure.
No, Paolo is the second. Paolo did his PhD in Groningen in the Netherlands, and he got it in 2008. Then he moved to Australia, to Astron first, and then Australia for some years. And then he came back to Italy with an ERC grant in 2016. And now he's in Cagliari as a staff astronomer there at the Observatory of Cagliari. And today he's going to talk about MeerKAT results on the Fornax cluster from the Fornax Survey. Grazie mille.
Okay, thank you, Rosita. Thank you all for the invitation and for being here today. So indeed, let me tell you about the MeerKAT Fornax Survey. This is a deep and fairly high resolution observation of a nearby cluster of galaxies called Fornax, using the MeerKAT telescope in South Africa at an observing frequency of about 1 gigahertz. And the goal of this project is to study how galaxy evolution proceeds in this particular cluster in the very nearby universe. I'll tell you why we are doing that in a moment, but first I'd like to acknowledge the great work of everybody who's been involved in this project, and in particular, those whose name is highlighted in yellow have been really instrumental in getting this survey off the ground, both in terms of development of data processing pipelines and the science analysis of this data. So you'll see their names coming up time and again during the talk. Now, the broad context of this project is our quest to understand the cause of the very strong connection between the morphology of galaxies, their properties in general, and their location in the universe. So their position within the large-scale structure of the universe or the cosmic web. The fact that such a connection exists has been known forever, essentially ever since the start of modern astronomy. Already people like Herschel, Shapley, and Hubble commented on the fact that the morphology of galaxies changes systematically depending on how strongly clustered they are with one another. And many colleagues have worked on this and have placed these results on very strong and solid grounds over the last many decades, and this work actually continues to this day. But to first order, the main observational effect is quite simple to describe, and it is that when you go from the lowest density regions of the universe, where galaxies live very far from one another, towards higher density regions of the cosmic web, like the nodes in this picture, the galaxy clusters, the morphology of galaxies changes systematically from the one that you see there on the bottom right to the one that you see on the bottom left. So in fairly low density regions of the universe, galaxies tend to have a late type morphology. They are full of young stars shining in blue and star-forming regions, typically distributed on a rotating disk. And as you move progressively towards denser regions of the universe, these morphologies, this dominant morphology, changes into the dominant morphology that you see on the bottom left, that of an early type galaxy, where you don't have these young stars, you don't have these star-forming regions. The optical morphology is very simple, very smooth and settled, the elliptical shape you see here on this slide, and the galaxies are dominated by all stars, so with a red color. And clearly the main difference here between the galaxies that dominate in low density regions of the universe and the ones in high density regions is one that concerns the cold star-forming interstellar medium, which is very abundant on the right and is nearly absent on the left. So the cold ISM is really the key here, and this will come up throughout the entire talk. Now, how you build this transition is actually what I'm very interested in, and what lots of significant part of the astronomy community works on at the moment. Now, it's good to try and simplify the very complex and very numerous processes that lead to this morphology density relation. And one way, you don't see the name down there, but one good way that I found that you can find in the literature is the one that is in this review by Luca Cortese from 2021, where you can group processes according to the time it takes to make a galaxy transition from this late type morphology to an early type morphology. On the top of this slide, you see very slow processes. Essentially, what you need to promote this transition in morphology is to stop the accretion and the cooling of gas onto the stellar disk of galaxies, a gas that comes in from the surrounding environment and cools from the circumgalactic medium onto the star-forming disk. You stop this accretion and this cooling, and that leaves you with a ISM disk, which will be slowly consumed through simply star formation. Because the depletion time of the ISM through star formation is of the order of a few giga-years, the decline of the star formation rate when you do this is very slow. It takes giga-years for this transition to happen. And I'll get in a moment into how you can actually do that. But this you can counter with much faster processes that quench star formation in galaxies on much shorter timescales. And these require the active removal of the interstellar medium from galaxies. Again, I'll comment in a moment about how you can do this, but many studies have shown that when you do that, in the regions from which you stripped the cold interstellar medium, the star formation rate goes to zero essentially within 100 million years. And so it's a much faster quenching compared to the several billion years that you see on the top. So understanding in which regions of the universe we have a dominant slow decline, slow quenching, say, and where you have a dominant fast quenching is one of the important questions at the moment. Now, how you can do that actually is illustrated here in an illustration by Eric Chang that has quite a few years now, but is aging well. What you see here is, the many different environmental processes, so the interaction between galaxies and the environment around them that can lead to this low and fast quenching. On the right-hand side of this slide, you see processes that require the interaction between the interstellar medium of galaxies and the intergalactic medium around them, which are shown in blue and red respectively here. This medium can be the intra-cluster medium if you're in a cluster, intra-group medium, but generally it's just all the gas that is around galaxies. And on the left-hand side, you see processes that have to do with the tidal interaction between galaxies and in general between galaxies and the gravitational potential within which they live. I won't go into all the details of all these processes, but one key fact that is very important is that the strength, the efficiency of these hydrodynamical, thermodynamical interactions between galaxies and the gaseous medium around them typically go with the square of the velocity with which galaxies move within the medium. Okay, and because galaxies tend to move faster within the medium as you move towards denser regions of the universe, these processes on the right-hand side, from pressure stripping, viscous stripping, and so on, tend to become more efficient as you move, say, towards galaxy groups and clusters and so on. The processes on the left-hand side, the merging of galaxies, generally the distortions that the tidal field can impose on the stellar body and the gas of galaxies, go on the contrary as 1 over v squared. So these processes are more efficient when the relative velocities between galaxies are lower. And therefore, these processes tend to become less efficient as you move towards denser regions of the universe where galaxies move faster. And so there is this natural expectation that as you move from low density regions of the universe to high density regions of the universe, you have a transition from a situation in which the processes on the left, gravitational processes, dominate, to one in which processes on the right dominate. Okay, that is the general expectation. We've done lots of progress through many different processes in trying to understand how this systematic change actually happens across the cosmic web, but a lot still remains to be done. Now, as I said, the key one of the key things here is what happens to the interstellar medium of galaxies. And the dominant component of the cold interstellar medium of galaxies is neutral hydrogen. So one key tracer of this transformation of galaxies is H1, observed through the 21 centimeter spectral line at 1.4 gigahertz. And that's essentially all that this talk is about. H1 has traditionally been a key tracer of this. Now the landscape has changed a bit. It's a lot more multi-wavelength, but H1 still remains a very important tracer for a number of reasons, but mainly it's the fact that it is distributed out to very large radii within galaxies. So it pushes into the region which is at the interface between galaxies and the environment around them, reaching radii where the gravitational binding to the host galaxy is weak. And so perturbing this galaxy is easy, this gas is easy. And also at such large radii, the dynamical timescales are long, and so H1 retains information of what's happened in the past for a very long time. And so that's why H1 is such an important tracer in this field. Here's a textbook example of a galaxy, for example, being stripped of its interstellar medium in the Virgo cluster. You see here an optical image. The black contours are the H1 in the gas disk. And you see the H1 being pulled out of the stellar disk, in this case because of the run pressure exerted by the intra-cluster medium of Virgo as the galaxy is moving towards the bottom left of this slide. And the beautiful thing is that we are now essentially at an age where making these images is becoming relatively easy for larger and larger samples of galaxies. Here you see an example of H1 maps in blue for Virgo galaxies in the Virgo cluster. You see the X-ray emission of Virgo in the background. And in fact, Francesco is here leading a project to take the next step compared to this work in the Virgo cluster itself. I'll show in a moment what we see in Fornax, but essentially this is becoming really a lot more common, and it's helping us understand how these processes of affecting the ISM of galaxies happens in different regions of the cosmic web. As I said, I won't touch too much on this during the talk, but as I said, this is now a very multi-wavelength field. H1 has historically been a prime observational tracer of these events, but nowadays we see the removal of the ISM from galaxies at a variety of wavelengths, going all the way to the X-rays, H-alpha with ionized gas, radio continuum. You see here on the right-hand side a beautiful result tracing the magnetic fields in the tail of stripped gas from one particular galaxy, from the gas project. There is lots going on and lots which makes, from my point of view, the H1 observations even more interesting because we can now combine with all these different traces and learn more. So, having said all this, the questions we'd like to answer are still fairly basic. We've done lots of progress, but in the end, what we'd like to know and what we still don't know for all environments in the cosmic web is what is actually quenching galaxies, what are the dominant processes as a function of position in the cosmic web, and how long does this quenching take. And our contribution to this at the moment is this MeerKAT Fornax survey, with which we are taking an approach quite complementary to that of other surveys that survey large chunks of the cosmic web, necessarily with high statistics, but necessarily with low level of detail. Our approach is quite complementary. We've chosen a particular region of the cosmic web, which is of interest for reasons I will tell you in a moment. And we are going very deep and good angular resolution on this particular region. Now, this region is the Fornax cluster. It's a nearby galaxy cluster. It's only 20 megaparsec away, so really around the corner. And it's important because it's close by, so we can study it in detail, but also because of its mass, which is fairly low, 5 times 10 to the 13 solar masses. And that places it kind of at the boundary between small clusters and large groups. It's an interesting region because if you remember what I told you earlier about this shifting balance between gravitational and hydrodynamical effects, it is in this region, this regime of masses, where we don't quite know what the balance is and what the interplay between different processes is. because it's a small cluster, the density of the intra-cluster medium is low, galaxies move relatively slow within it, so hydrodynamical effects might be weak. And at the same time, galaxies move relatively slow to one another, and so their tidal interactions with one another are very effective. And so what we'd like to understand for this cluster is, again, fairly basic stuff to begin with. Can we find any direct evidence of galaxy transformation in a small cluster of this kind? And if so, what are the physical processes that are driving this transformation? So what we knew before the MeerKAT Fornax survey about H1 in Fornax is the following. This was the state of the art before these MeerKAT observations. You see here a large field centered in the Fornax cluster. The magenta line is the X-ray emission, mapped, I think, in this case with XMM Newton. You see the brightest cluster galaxy, NGC 1399, in the center. And the large white circle is the virial radius of the cluster, which is about 700 kiloparsec. Towards the bottom right, you see another circle. That's a virial radius of an infalling galaxy group, which is centered on NGC 1316. You'll see it later in a moment. And the yellow outline here is the footprint of this particular survey done with the Australia Telescope Compact Array a few years ago, and published by Alessandro Loni in 2021. And in green here, you see the 16 H1 detections from this data. And if you think back of the kind of H1 features I showed earlier, this was essentially the only one galaxy where we saw something that seemed interesting. You see the H1 in white and in green contours here, and a tail of gas probably being removed from the galaxy because of the interaction with the environment, with the cluster environment. But the resolution of this data and the sensitivity were not good enough for us to actually conclusively even say what kind of interaction was taking place here. What we're doing now is to cover the same region with MeerKAT. Each of these crosses now is a MeerKAT pointing. There are about 90 of them. Whenever you point MeerKAT at the sky, you observe a field of the order of a square degree at 1.4 gigahertz. And so you see that there is significant overlap between these pointings, and that is one of the ways in which we build our sensitivity. So we're making a mosaic, radio frequencies, both H1, but also radio continuum and polarization, if you're interested. And essentially, it is as if at each position of the mosaic, we were integrating for 30 hours with MeerKAT. So they're very deep observations. You see here also the progress of the survey. The green crosses are for fields for which we have science-ready data. In fact, we have a mosaic of that entire region. That's about 70% of the footprint. The orange ones we're still processing, and the green ones, the gray ones, sorry, we are actually observing, and the plan is to complete the survey essentially at the end of this year, within a few months, basically, 1 or 2 months. So we are now busy with this region, which is quite interesting, of the infalling group centered on NGC 1316. And in fact, I want to highlight that we had already looked at this region before we started the survey, before 2020, when we were busy helping commission the telescope. And we've published a number of papers on that. I won't go into the details, but I'd like to showcase this beautiful image coming from our work and our collaboration with amateur astronomer Ferrante Enriquez, who's based in Milan and operates a telescope that is in the desert of Namibia. And it takes these beautiful images. So what you see here is an optical image showing all these shells and ripples of stars. And overlaid on that is our radio continuum image of Fornax HI in NGC 1316 at the center of this infalling group made by Filippo Maccagni with MeerKAT commissioning data. You see these beautiful lobes of this radio source, and in blue you see the H1. And during the past few years, we've published a number of papers dealing with the interaction between galaxies in this group, which is quite evident, if nothing else, already from the optical image. The nice work by Filippo Maccagni is here in the audience on the flickering of the AGN at the center of Fornax HI on timescales of the order of 10 million years or so, caused by the recursive infall of cold gas towards the central black hole. And also quite interesting work by Francesca Loi. If you see the gas there towards the top right in blue overlaid on top of the radial lobe, that is H1 gas that is in between the radial lobes and us. And it has a depolarizing effect on the radio continuum emission from the radial lobe, which allowed us to tell us something about the magnetic fields that is interaction between galaxies in the groups are injecting into the intragroup medium by simply throwing ISM with the associated magnetic field into the group. So check out these papers if you're interested. But I'll move back to the actual survey. And so I'll show mostly results now from the region that you see in green here, this region for which we have science-ready data. That's a slightly technical slide just to show the kind of sensitivities we're reaching. I appreciate that there aren't many H1 astronomers here, but let me explain what this means. Here on the left and on the vertical axis, you have the H1 column density sensitivity in atoms per square centimeter as a function of resolution in kiloparsec. One great thing of MeerKAT is that it allows us to make data, make H1 images, cubes, radio continuum is the same, over a wide range of resolutions, roughly between 10 and 100 arc seconds. The sensitivity of the telescope is great. And so we can cover these different resolutions in kiloparsecs now at the distance of Fornax. And at the different resolutions, we go down in H1 column density sensitivity, as you see through the stars that are the values we measured for our H1 mosaic. The red was the expectation. Okay, so we are spot on what we wanted to do, which is telling you something about how great MeerKAT is, but also about the quality of the data processing we did. And so with this kind of data, we can trace and we can study the H1 at relatively high column density at resolutions of the order of a kiloparsec. That's where you see the dense H1 where stars are forming. But then going all the way down to roughly 10 to the 19 atoms per square centimeter, that's where you trace gas at the outskirts of galaxies, and so at the interface between them and the surrounding medium. That's where you see extraplanar gas. That's where you see the features tracing the removal of gas from galaxies. And then all the way down to 10 to the 18 atoms per square centimeter, which is to some extent uncharted territory at these resolutions. And you see there the green dot is the previous H1 observations done with a compact array in Australia. And just a quick advertisement that we're doing this using this Caracal pipeline to process the MeerKAT data. There's different kind of software involved in all this. Another one that I'd like to advertise is Sophia, which is a source finder for spectral line, which is used quite heavily in the H1 community, but also more and more in the ALMA community, for example. And so with this fantastic data, we go from this picture of Fornax that we had with the ATCA data to this one here. So if I go back and forth between the two, you see the difference in the level of H1 detections we have. And so now with our MeerKAT eyes, we see lots of H1 clouds, tails of H1 associated to many galaxies in Fornax. There is H1 essentially all over the place compared to the view we had before, which is telling us, giving us a first answer to one of the first questions I posed. Can we see any ongoing evolution in a low mass cluster like Fornax? From the ATCA data, the answer was, well, maybe. And here the answer is very, very, very clearly yes. Still now, at redshift 0, these clusters are doing lots of things to the recent members that are unfolding now in them. So one first result I'd like to discuss is what these features, the H1 features, are teaching us about what kind of processes happen in these low mass clusters. And this is the results from a paper we published last year with a sample of galaxies with clear H1 tails sticking out of the stellar body of these objects. And these tails have very important properties that tell us, how they are forming. They are all one-sided. Okay, They're all starless with very deep optical images. There is no all stellar counterpart to these tails. So whatever is shaping them is able to displace only the gas, but not the stars. And they're all radially oriented within the cluster. Some of them are pointing towards the center, some away from them. But if you see these arrows pointing towards the center of the cluster, all these tails are radially oriented. And these are all the kind of properties you expect in case of run pressure stripping, because when a galaxy enters a cluster, statistically, typically enters a cluster on a radial orbit, so it points straight towards the cluster and then away from it when it's past very center. And therefore, you would expect tails of run pressure stripped gas to be aligned radially. You expect them not to have stars because run pressure only acts on gas, not on stars. And so these are all, these observations are entirely consistent with these tails being shaped by run pressure. Another important thing we can look at to test this hypothesis of run pressure is the velocity gradients along the tails. Here you see these velocity fields of the H1. So the color is coding the velocity of the H1 gas along the line of sight. And if you take, for example, the galaxy on the top left, this galaxy is strongly blue shifted within the cluster by about 500 kilometers per second, 1.5 times the velocity dispersion of galaxies in the cluster. So it's moving towards us along the line of sight. And so it's experiencing a run pressure wind that is pushing gas towards redder velocities. And indeed, as you move along the tail, the velocity of the gas is becoming more and more red. And you see that in these other objects. So this is another important consistency argument that these tails are indeed being shaped by run pressure. They're being shaped by run pressure, but they are probably not caused by run pressure to begin with. And I'm saying this because all these galaxies, when you look at them in optical wavelengths, they look fairly disturbed. Okay, that's something you don't necessarily see in a bigger cluster like Virgo or Coma, where you see tails of run pressure stripped gas on galaxies that optically look fairly undisturbed. These galaxies all look like something that's happened to them in the recent past, to their stellar body. And so it seems that having had most likely a recent tidal interaction, and so having had your stellar body shaken and stirred in some ways, is a necessary condition for a galaxy to then develop a long tail of H1 stripped by run pressure. And so our idea is that in a small cluster like Fornax, where you expect hydrodynamical effects to be relatively weak, you first need kind of a tidal trigger. You first need these galaxies to undergo a tidal interaction, which loosens the gravitational binding of some of the gas compared to the host galaxy. And once this gas is more weakly bound to the host galaxy, it's easier for the relatively weak run pressure of Fornax to sweep up this gas and create the tails we observe. Getting into more details of this, this is a recent paper we published a few months ago showing for one particular galaxy, this NGC 1427A here, to what extent we can trace the detail of this sequence of events with this data. So what you see here on the left is the H1 contours at different resolutions. And you see towards the top right, the stellar body of the galaxy. On the right-hand side, you see a position velocity diagram of the H1. So let me explain what this is. You take the segment, this line traced by the blue arrow on the left. And as a function of position along this path, you show the H1 spectrum on the vertical axis. So this builds this position velocity diagram where you see essentially where you have H1, at what velocity you have H1 as a function of position along this. You see on the right-hand side of the position velocity diagram, you see bright H1. That's where you are on the stellar body itself. And then you see this long H1 tail pointing towards the bottom left in the position velocity diagram. This gradient is what you'd expect based on the motion of the galaxy within the intra-cluster medium. That's a gradient that is caused by run pressure. This galaxy is very strongly redshifted relative to the intra-cluster medium. And so gas gets progressively more and more blue shifted as you move towards the edge of the tail. But then what you see if the gas had been stripped by run pressure to begin with, it would immediately start to accelerate into the run pressure wind right from the start. So you'd have this gradient making it all the way into the stellar disk. But instead, you see an inversion of the velocity gradient there, closer to the main disk. And that is completely inconsistent with run pressure. You can't do that gradient with run pressure. And so this is again telling us that something else must have happened. And for a number of reasons we go into this paper, what we think is indeed first a tidal interaction with another galaxy in the cluster itself. And then later, this, as I explained earlier, this disturbed gas has been displaced further by run pressure. Now, with this kind of data, we can do more than just looking at the states. We can actually look how far into the stellar body hydrodynamical forces can have an effect on the interstellar medium of Fornax members. This is again the same object. Here you see on the left-hand side the velocity field again of the H1, but now focusing on the inner part of the galaxy, on the stellar disk. You see on the right-hand side the optical image of the galaxy with the same kind of isophotos shown for reference. And if you are familiar with H1 velocity fields, with velocity fields in general, you might notice this bending of the line of nodes, the line of nodes being the line of maximum and minimum velocity. So tracing the position of the major axis of the galaxy, the kinematical major axis, you see that it bends, follows an S shape, which you see also in this model on the right-hand side. This is simply telling you that the orientation of the circular orbits is changing as a function of radius within the galaxy. Basically, the angular momentum vector of the circular orbits is changing direction as you move towards larger radius. That's giving you this S shape. But in the model on the right-hand side, you see also that while we can match that shape of the line of nodes, we don't match another important feature, which is the location of this green line. That's gas at the systemic velocity, which when you have a warp of this kind, this changing of the angular momentum direction, is also following an S shape, as you see on the right. And that's not what we see there. What we need to match the data on the left is to add a velocity kick to all of the gas in the galaxy, all the way inside, down to one effective radius. Further in, we don't see evidence of that, but down to one effective radius of this galaxy, we need a velocity kick, which is entirely consistent with our analysis of run pressure based on the H1 tail. So we see that run pressure is actually able, in this case, to displace the gas also in the relatively inner part of the stellar body. Okay, that's the detailed view of one or a few galaxies. This is the H1 in a relatively central region of the cluster on top of a deep optical image. Other than tails, and I've discussed them at length, we find H1 clouds associated mostly with galaxies a bit everywhere in the cluster. H1 clouds, dwarf galaxies detected in H1, with H1 masses all the way down to 10 to the 6 to 10 to the 8 solar masses, so very deep observations. Hundreds of dwarf galaxies are undetected in Fornax. The vast majority of them are undetected. And so clearly something is happening in a low mass cluster like this one to dwarfs. That's something we've been investigating now for a bit. An interesting result is from this paper by Dane Kleiner from last year. So let me guide you through this plot. What you see here is H1 mass on the vertical axis and optical luminosity or absolute magnitude along the horizontal axis, just for dwarf galaxies. Okay. In the field, outside clusters, there is a very clear scaling between these two quantities. Now, the brighter you are, the more H1 you have. And that's shown by the gray diamonds. These are field galaxies, dwarf galaxies in the field. And the interesting thing is that when you look at the late-type dwarf galaxies in Fornax, these are dwarf galaxies that are still blue, forming stars, full of knots. Their H1 properties seem to be consistent with what we have in the field. So these must be very recent arrivals. It's full of dwarf galaxies along the entire horizontal axis. It's full of dwarf galaxies that we don't detect in H1 in Fornax, but there are basically no galaxies in between. You either have H1 as much as you should have if you were in the field, or you don't have any. Okay, and that means that the transition between the two regimes must be very, very fast, which is what you'd expect in a cluster of galaxies. But we're seeing now this transition happen. And then below a certain mass, below this absolute magnitude of -14 or so, we stop detecting dwarfs. Okay, even late type dwarf galaxies, so dwarf galaxies that are blue, they still have knots of young stars or star formation. These are all these colored circles here. They don't have any H1, and it's not because we're running out of sensitivity. Our 3 sigma upper limit is that red line. We find galaxies that are blue still, dwarf galaxies that are blue in Fornax, but that have 10 times less H1 than they should. And again, this is probably telling us that the H1 goes very quick. In a cluster like Fornax, it goes very quick from a dwarf galaxy, so quick that you stop detecting it while the stellar population still has to age. And so it's still blue and still showing the clumpy feature of a star-forming dwarf. Another way of seeing this rapid removal of H1 from dwarf galaxies in Fornax is our study of the H1 mass function. This is work by the incliner again in preparation. What you see here is the H1 mass function. So you're simply counting how many galaxies have a certain H1 mass running on the horizontal axis. And if you focus on the blue circles here, these are our measurements for Fornax. Okay, it's just one cluster. The statistics is low, but because we're going so deep, in fact, our detection limit is 5 times 10 to the 5, we can trace the slope of the H1 mass function quite well. And the fit to our data is the black line with the gray shaded areas for the uncertainty here. And you see that this is completely consistent with the orange line, which is the H1 mass function in the field, up to a point, roughly 10 to the 7 solar masses, after which the H1 mass function in Fornax just collapses. These are the last 2 points. We essentially stop detecting H1 at that level. And again, as I said in the previous slide, this is not because we're running out of sensitivity. Any mass function will always start dropping at some point because you hit your completeness limit. When our mass function starts dropping, we're at a 40 sigma detection level. Okay, so literally these galaxies, they should have 10, 20, 30 times more H1. They don't have any. And this is the first time actually we're seeing something like this. The H1 mass function has been for a couple of decades a way for us to study the impact of the environment on the galaxy population. The focus has always been on measuring a change of slope of the mass function, the expectation being that you start from the mass function in the field, and because low mass galaxies are the ones who start losing gas first, you tend to flatten the slope. This has been attempted many times. What we were seeing now, at least in Fornax, is that the slope is the same. That's not the main thing that is happening. What's happening is that at some point, your mass function stops being affected, and it just truncates. Where this truncation level happens might depend on the cluster, but that might be the main thing that happens in clusters. And clearly, there is a lot more to do in the future on other environments and in simulations as well. We see indeed that these dwarf galaxies are quite strongly affected by the cluster environment. This is a recent paper by Nikki Zabel, where she's combined our MeerKAT data with Muse data. You see the stellar velocity field on the top left and the H-alpha velocity field on the bottom left. And ALMA data, you see the molecular gas velocity field on the bottom right. And the main message here is that the ISM of these tiny objects in Fornax is quite a mess. There is a clear unsettled distribution of the gas, with the different gas phases actually doing different things relative to one another. And I'm not completely sure we fully understand all of that, but it's work that is starting. And the final thing, the final 2 things actually I wanted to advertise. One of them is that we are now starting to combine this data with data at other wavelengths. And one thing we're very interested in is to look at the stellar populations and star formation histories of these galaxies. Because the H1 is great, because it helps us to diagnose the physical processes, as I hope I've convinced you of, the physical processes that are happening in these clusters and this sequence and interplay and balance between different kinds of interactions. But it doesn't always tell us a lot about the time scales. Well, if you look at the star formation histories, you can actually follow what happened to the star formation rate of galaxies as a function of time and try to connect those with what we see in H1. So this is something that Alessandro Loni published last year. You see a galaxy in Fornax that has a truncated H1 disk. The H1 is a black contour here, and the H1 disk is completely confined within the inner part of the stellar body, which is very unusual. So this galaxy has a star-forming inner disk, and then it's surrounded by a completely quiescent early type-like stellar body. And using Muse data, we could look at the star formation history of these two different regions, the inner part of the galaxy and the outer quiescent one. And what we find is that essentially in the outer part, there has been a very fast quenching of the star formation, as if the gas has been removed very quickly and star formation stopped. While in the inner part, star formation is still happening and is declining at a very low pace. And that's more or less what you expect in a cluster of galaxies. Up to a certain radius, where the gravitational binding to the host is strong, you can't do much to the ISM. So you simply stop accreting more gas and the star formation rate declines slowly. While from that certain radius out, where the gas is less strongly bound, you remove it fast and you quench star formation very fast. And it's beautiful to actually see it in the data. And so more of this is coming up through the combination with Muse data, like in this case, from Fornax 3D. But there is also a beautiful optical survey called S+, nowadays that we are combining also data with. Final thing I wanted to really just advertise and not discuss much is that there is a radio continuum component to this survey, of course, which includes polarization, rotation measures, sorry for the misspell there. This is led by Francesca Loi in Cagliari. There is a paper currently under review with the rotation measure grid of the cluster with about 500 RM measurements. So a density of about 80 sources per square degree, which is really SKA regime for this kind of work. So stay tuned for that. And I'll end here. So the main results up to this point is that we are detecting, we're finding an answer in a sense to our very basic first order questions we started with. We're finding ubiquitous H1 tails and clouds in the Fornax cluster, which reveals the ongoing evolution of first infolders into Fornax as a result of the interactions within this environment. We think that the interaction with the environment in Fornax happens in two steps. First is tidal interactions that pull some of the H1 out to large radius, loosen the gravitational binding to the host, and then makes gas more susceptible to the weak run pressure of a low mass cluster like Fornax, and then indeed hydrodynamical. We're also focusing on low mass galaxies. They're very interesting, and we're finding that the removal of H1 from these must happen very fast. We see this in their properties, one by one, and in the H1 mass function. And the last point, I think we're going to do a lot more work on this to try and connect this H1 data with other properties of this galaxy, and in particular the star formation history, to constrain not only the physical processes, but also the time scales on which they are operating. I'd like to conclude by saying that all the H1 data we've published are available on our project website. So if you're curious, go and get them. Thank you.
Thank you very much. Always enlightening. There is time for questions. Yeah. Excellent. Sorry.
Thanks, Paul. So which is the total mass of H1 that is associated with Fornax, also including the part that is apparent is probably heated up during the falling down in the system?
So the total H1 mass of the, adding up all the galaxies, it will be of the order of 2 times 10 to the 10, which is actually, it's tricky when you have few galaxies. Essentially, I think most of the H1 is actually in this one galaxy, the only one big spiral of Fornax. Right? That's where most of the H1 in the class is.
About 10%.
Yeah.
Then if you include also all the H1 that disappear in a mass system, then you find into 6 classes.
It's still not going to change too much because if you integrate your typical H1 mass function, most of the H1 is in the big galaxies. There's never a lot of H1 in the dwarfs.
Beautiful talk, share was right. And I have 2 questions. One, sure, you don't expect to see all stars in the gaseous state from pressure state, but usually you see presence star formation. You see the chalcophanes or blue stars. You see those even in your days, or they are completely devoid of stars?
We're working on that. When you said that usually you see young stars in the tails,
Yeah.
I think there are spectacular many objects where you do see that, but I think we're a bit biased in the current in current years in particular. We're a bit biased in that. There's a beautiful project like GASP, for example, where you see lots of this, but those galaxies are selected in essence to have that because they were selected on broadband imaging to see the stays already in blue light, and so sure enough you'll see the star formation. And they are very important. It's an important family of objects. How common that is, I don't think we know. In these objects, we don't really see much of that. We're currently taking H-alpha data. In fact, we've taken H-alpha data with the VST. The PI was Filippo Maccagni to exactly observe this. We've taken also very deep UV imaging with UV. And in the best of the cases, we see very little bit of star formation in these galaxies. So, this is very interesting in itself. It could be that you need exceptional conditions in order to trigger star formation in these states. And maybe the kind of speeds involved in Fornax, the kind of density of the ICM are not high enough, dramatic enough to actually trigger star formation in the state. That's my current view.
Second, very quick. Do you find any H1 cloud that is devoid of stars? Dark cloud?
We do. You see them here, for example. Actually, let me see if I have. Well, you see this collection of clouds down here, for example. These are all devoid of stars. And let me actually try and get another plot to make this point better. If I find it. Maybe I don't. The point is, these clouds don't seem to be like, you see them also here. 2 things I wanted to say about these clouds. One is that in most cases, they seem to be connected to galaxies. Okay, you see here NGC 1427A, the galaxy discussed in detail. Those tails, those clouds already are at the same velocity, and they, in fact, they continue the velocity gradient you see in the tail. So we think they are essentially the leftover of the passage of the galaxy through the ICM. They don't have optical light down to very strong limits. What I wanted to show you, but I don't find the plot, is that there is a clear gap in optical luminosity between the dwarf galaxies with similar amounts of H1 and the upper limit on the luminosity of these galaxies. These are like 10 to 100 times fainter, so they're not a continuation of the dwarf population. And the other thing is that what they look like, also in terms of the gap between them and the tail that they originate from, they have many properties that are similar to those of simulations where you have the tails of stripped gas caused by the mixing with the ICM. So I think they're very interesting objects to study the mixing between the ISM and the ICM in clusters.
Thank you very much.
Rosita, we was Fabio online with the questions.
Yes, can you speak? Yeah. Yeah, Fabio, you can ask your.
Yes. Very nice talk, stunning data, Paolo. I don't know if I missed it, but the tidal field is the one done by the cluster mass, or do you need also galaxies around?
No, it's a good point. In the case I discussed in detail, this galaxy in GC 1427A, we went through the numbers, and the tidal field of the cluster as a whole is not enough. Basically, you can calculate the tidal radius, and in that particular galaxy, the tidal radius doesn't even make it to the edge of the stellar body. It's way out. So I think the tidal field of the cluster will have an effect on galaxies with a stellar mass below 10 to the 8 solar masses in Fornax. That's our calculation. Above 10 to the 8 solar masses, the galaxies are too big. And so these tidal effects I'm talking about are mostly through mergers and interactions with other flybys, maybe, with other galaxies in the cluster.
There is also
Sorry, there is another one online, and then we go back to the room. Please go ahead.
Thank you so much. Thanks, Paolo. Interesting result. That was amazing. About the last few slides that you showed, the star formation history, it's been shown that in those galaxies that are affected by ramp pressure or other phenomena, there is a starburst at some point, because also those ramp pressure can contract the gas within the disk. And then also the starburst helps the amount of stripping gas to go out of the galaxy. So based on this time scale that I'm seeing here, basically that happens in the 3 gigayear to 4 gigayear ago. Do you think this time scale of quenching, which shows the time scale of the how long it's been that it's been affecting by those effects, compatible or aligned with what you expected from those systems, or it's too long?
No, I think that's more or less right. In this one case, though, I don't think that burst is called by ramp pressure because it's too strong. If you look at the one on the top, the burst on the star forming disk is very strong. So
Nice.
But I think you're right. Ramp pressure can trigger this. It connects a bit to the previous question where star formation in the tail, but also in the disk itself. But not in this one case. I think my impression, but it's a bit speculative in this case, is that this galaxy probably formed through a relatively major merger of two galaxies falling together inside Fornax. That could have triggered a strong burst like this one. And then during a merger, then what happens is that you have the inflow of gas, that's the burst, but you also have tidal tails, okay, going out to large radius. And there is enough time since the burst for this tidal material to fall back into the galaxy, but you're inside a cluster, so you only reaccrete a stellar disk, but not an H1 disk. And I think that's why we have the morphology we have in this case.
Oh, that's interesting. So this is not the typical behavior that you see in those types of galaxies. These are just by accident. These two galaxies that you're showing here are only happened by accident. That the starburst in the relatively near
I
past.
don't think it's by accident. I think this might be a very common channel for galaxies to evolve in a cluster of this mass. Again, because of the dispersion being low, mergers are common, and on top of those, ramp pressure happens.
I understand. Thank you, Bob.
So I think we have time for another question.
No, maybe I didn't understand. You said first tidal, then hydrodynamical. So does this mean that you have cases where you don't have the first and then you also don't have the second? Or
in Fornax, that is true. We don't see indications of ramp pressure in galaxies of this size, say above 10 to the 9 solar masses. We don't see signs of ramp pressure in galaxies that are not tidally perturbed.
So you have H1 detections, but without the ramp pressure.
Yes, we have H1 detections without the ramp pressure. Then I stressed above 10 to the 9 solar masses. Lower mass galaxies, we do see that. I haven't shown them. We have a few cases of one-sided H1 asymmetries or tails in galaxies that look normal in the optical. but they are tiny. So these are galaxies where run pressure, even though it's weak, strong enough for them to do some damage, even without a tidal trigger. So it's mass dependent.
Yes, if there is any very quick question, I don't know, Viviana, thanks.
In addition to NGC 1365, how many spiral galaxies are mapped in each one by the whole Fornax survey?
Let me take you back. To, yeah, here. So here, real late type, properly blue star forming. In this region of the cluster is 2, 1365 and ISO 35860. That is a strange galaxy because it's got a huge H1 disk compared to the stellar body, completely settled, nothing is happening to it. And we now have a paper under review where we show that, in fact, if you put it on the Tully-Fisher relation, it's outside the cluster. You can measure its distance, that's why. If we go towards Fornax A, then that group is dominated by late type galaxies. So that there are more, and we are starting to study them now. And
Okay, it's quick, then.
Very quick. So did you try to convert the H1 mass to star formation rate and compare these results to the study of the star formation main sequence? Because people in that sort of environment, they call this the delayed then rapid quenching scenario. And it is the same that you explained, but seen from the point of view of the star formation rate.
yeah, I think there is a strong connection with that indeed. We are starting to do that. And you see here star formation rate versus stellar mass. The color points are galaxies, you know, with different flags according to the morphology. So they are, and that's an H1 mass versus stellar mass plot. They're typically a bit depleted in star formation rate, a bit lower, you know, below the mean sequence, but they're also a bit lower in H1 mass. And the two things seem to be going kind of hand in hand. Also in the field, if you have galaxies with a bit less H1, they have a bit less star formation rate. And I think the fact that they're depleted in both is, again, consistent with what we're saying about this low, relatively slow evolution, delayed, and then all of a sudden it's happened.
Okay, I think now we can thank again Paolo. The full afternoon, fourth floor at Ira, if you want to chat with him, or during the lunch time.
Poi ti vediamo all'Ira oggi pomeriggio.
Sì, sì,
Abbiamo un borrel.
Sì, vengo, mi hanno detto
bella.
che c'è il...
E io ho una lezione che devo fare, ma magari sul finale vi racconto. Non vi trovo ubriachi, sì.
Speriamo.
Sì.